Hey guys, this video is on solids, and in particular something called crystalline solids. So there's crystalline solids and there's amorphous solids. Crystalline solids are ordered. They have an ordered arrangement, and that comes from this pattern that's repeated at the atomic level. An example of a crystalline solid would be diamond, and you can see the result of the order at the atomic level in diamond because, first of all, diamond is made up of just carbon atoms, and when you cleave a diamond, you get these nice shiny faces, which is a result of the bonds breaking along the edges of what makes up the order at the atomic level, called a unit cell. Now, amorphous solids, they don't have any underlying pattern, no long-range order, they're messy. Coal, which is also just carbon, just like diamond, is an example of an amorphous solid. If you try to cleave diamond, it pretty much just smashes. So, unit cells are what give crystalline solids their order. And what a unit cell is, it's the simplest pattern that when you repeat it in 3 dimensions gives the order to the crystalline solid. A real simple example of a unit cell would be this cube right here. Now each of these blue spheres, it represents an atom on each of these corners. There's 8 corners. So if you take a bunch of cubes like this and you stack them up, you get the result is a crystalline solid. Just like if you can think in 2 dimensions. If you think about tiles on a floor, just kind of the same idea. Or building blocks if you use those. Now there's 7 types of unit cells: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. We're only going to focus on the simplest, which are called cubic unit cells. The way a unit cell is defined is by the length of its sides. So we label them A from here to here, B from here to here, and C from here to here, as well as its angles. So alpha, which would be the angle between C and B, beta, the angle between C and A, and gamma, the angle between A and B. And for us, it's just a regular cube, which means that the lengths of all the sides are equal, A equals B equals C, and the angles are all 90 degrees. When you start changing that, you get different unit cells. So there they are, but we're going to focus just on the top 3. So these are the top 3 unit cells: simple cubic, body-centered cubic, and face-centered cubic. Back here, this is not very representative of what it actually looks like in the real real solid, but it makes it easier to see where the atoms are. So in a simple cubic, we just have 8 corner atoms making a cube. In a body-centered cubic unit cell, we have 1 atom that's in the middle that's entirely enclosed within that unit cell, and then 8 atoms on each of the corners, like a simple cubic unit cell. It says primitive cubic, same thing. So that's a body-centered cubic unit cell. In a face-centered cubic unit cell, what we have are 1 atom on each of the 8 corners, plus on each of the 6 faces, there's an atom that's half in this unit cell and half in an adjacent unit cell. Body-centered cubic unit cells have what's called hexagonal close packing, or they're hexagonal close packed. Face-centered cubic unit cells have what's called cubic close packing, or they're cubic close packed. Now, the efficiency of the packing increases from left to right in this picture. A body-centered cubic unit cell with hexagonal close packing utilizes more of the space. There's less empty space than a simple cubic unit cell. Now, a face-centered cubic unit cell with its cubic close packing uses even more of the space. There's even less empty space in a unit cell. So here's how the packing goes. In hexagonal close packing, if you think about laying down 1 layer of atoms and then taking a second layer and putting them in the holes of the first layer. And then the third layer go in the holes of the second layer directly above an atom in the bottom layer. So you get these repeating layers, A, B, A, B. Now in cubic close packing, you don't repeat until after 3 layers. So if you think about this layer as being on top of a bottom layer, so layer A is on top of a bottom layer, and it's in some of the holes on the bottom layer. And then you take the layer B, the next layer, put it in the holes of layer A, but the holes that are not directly above the atoms in the bottom. And then when we get to layer C, now these atoms are directly above the atoms in the very bottom layer. So we don't repeat until after 3 layers. We have A, B, C, like that. If you have any spheres that you have enough of, like if you have some oranges or tennis balls or something like that, you can see this yourself. Just you don't need that many. Just put lay out some on the floor, and then put the next layer on just like this, and then play around with it, and you should be able to see this. All right, so a coordination number for a unit cell is how many atoms each atom in that unit cell is touching in direct contact with. In a simple cubic unit cell, its coordination number is 6 because every atom in that simple cubic unit cell, which is what this is representing, here's one unit cell, 1, 2, 3, 4 on top, 1, 2, 3, 4 atoms on the bottom. So if we look at this atom in here, it's touching 1, 2, 3, 4, 5, 6 other atoms. Its coordination number is 6. Now the higher the coordination number, the more efficient the packing in that unit cell. Now, in a simple cubic unit cell, there's only 1 atom per unit cell. Now, I know it looks like more because look at all these spheres, but each of these corner atoms is not entirely in just that unit cell. There's 8 corners, and each of these is just actually an eighth of an atom. And maybe it's a little easier if we come over here and look at this. If we look at this atom that arrow's pointing at, it's actually inside of 8 unit cells. So if this unit cell over here, okay, that's 1, this part in there. That unit cell right in back here, 2, it's also in that unit cell. 3, the one back here, part of this atom is in that. 4, the front unit cell here, part of this atom is in this unit cell too. And the 4 beneath it. This unit cell here on the bottom, part of that atom's in there. This unit cell down here, part of that atom's in it. The unit cell in the back here, part of the atom's in it, and 8 over here is also in that. So because there's only an eighth of an atom in that unit cell per corner, and there's 8 corners, we have 1 atom per unit cell. Now, so the coordination number for a simple cubic unit cell is 6. For a body-centered cubic unit cell, it's 8. And that's because each atom touches 4 atoms above it and 4 atoms below it. So it's easiest to see that if you look at the center atom in a body-centered cubic unit cell. It's touching the 4 atoms on top and the 4 atoms on the bottom. For a face-centered cubic unit cell, the coordination number is 12. It's even more efficient. Each atom touches 6 atoms in the layer it's in, 3 atoms in the layer above it, and 3 atoms in the layer below it. So in a simple cubic unit cell, there's 1 atom per unit cell. In a body-centered cubic unit cell, there are 2 atoms per unit cell. The 8 corners each has an eighth of an atom in it, just like a simple cubic unit cell, plus the atom right in the middle. So 1 from the corners plus the 1 in the middle is 2. In a face-centered cubic unit cell, there are 4 atoms per unit cell. There are 6 sides. Each of these sides has 1/2 of an atom. So 6 times a half is 3. Plus 8 corner atoms, each with 1/8 of an atom. 3 plus 1 is 4. That's useful information to remember how many atoms per unit cell for each of the different kinds of unit cells. All right, so now, if we know the atomic radius of an atom and what type of unit cell it forms, we can calculate the density. Because, remember, density is mass over volume. So we need the mass and the volume. The volume for a cube is just the side of the length of a side cubed to the 3rd power. So, but because now it's not true for the other unit cells, but for a simple cubic unit cell, the atoms are touching. So this is 1 atomic radius, this is another. So the length of a side of a unit cell in a simple cubic unit cell is equal to 2 times the atomic radius. So if we know the atomic radius, multiply it by 2, that gives us the length, which gives us the volume. Now to get the mass, okay, if we know what element it is, we can just take the molar mass from the periodic table and divide by Avogadro's number, 6.022 times 10 to the 23rd atoms per mole, and multiply that by how many atoms there are per unit cell. And that will give us the mass of 1 atom. So let's use that. Let's do a little example here. So solid oxygen, actually there's a couple forms of oxygen. This is metallic oxygen. It's pretty cool. If you put enough pressure on oxygen, you can make it a metal. And it forms a simple cubic unit cell when you do that. given that the atomic radius of an oxygen atom in metallic oxygen is 135 picometers, calculate the density of solid oxygen, metallic oxygen, in grams per cubic centimeter. So go ahead and work this out if you would, guys, and when you get an answer, come on back. Welcome back. So here's the approach. We want the density, which is mass over volume, so we need the mass and the volume. The volume of a cube is the length of a side to the third power, and the length of the side is 2 times the radius. So we know the atomic radius, so we can get L, which means we can get V. Now for the mass, it's just the molar mass. We know that it's oxygen, so we can look up its molar mass, divide by the Avogadro's number, times the number of atoms per unit cell. Simple cubic, 1 atom per cell. So, all right, so let's do it first. And because we want this, we're given the radius in picometers and with the density in grams per centimeter cubed, we're going to want to convert to centimeters. So I'm going to do that right away. So 135 picometers, 1 meter is 1 times 10 to the 12th picometers, and it's 100 centimeters. So there's 100 centimeters per 1 times 10 to the 12th picometers, which shows us that the atomic radius is 1.35 times 10 to the minus 8 centimeters. Now we multiply the radius, the atomic radius, times 2 to get the length of a side of the unit cell. So we get 2.70 times 10 to the minus 8 centimeters. And now we just cube that to get the volume of a unit cell, 1.968 times 10 to the minus 23rd cubic centimeters. Now, okay, so that's our volume part. That's the bottom here. Let's get the mass. Okay, it's just the molar mass. Now this is atomic oxygen. It's not a diatomic. When it's a gas, it's O2, but here it's just O. So 15.999 grams per mole divided by Avogadro's number shows us that the mass of an atom of oxygen is 2.6567 times 10 to the minus 23rd grams. And there's 1 atom per unit cell, so the mass per unit cell is the same number. Now we have the mass of a unit cell, the volume of a unit cell. All we have to do is plug in, and we get 1.35 grams per cubic centimeter. And if you look up the density of metallic oxygen, it's like 1.362 times, 1.362 grams per centimeter cubed. So pretty good. All right. So the relationship between atomic radius and the length of the edge of the unit cell is a good thing to know for all 3 unit cells. We already know for a simple cubic unit cell. Here A represents the length of a side of the unit cell. It's just 2 times the atomic radius. But in a body-centered cubic cell, the atoms on the corners are not touching, so it's not 2R. So what we do is we set up some right triangles and use the Pythagorean theorem. So for this right triangle here, this side is A, this side is also A, which represents the length of a side, and this is a diagonal that goes from this corner up to this corner on this face. And that's going to be, the Pythagorean theorem says that b squared is equal to a squared. Well, a squared plus b squared equals c squared, but here a and a are the same. So this length, b squared, is equal to a squared plus a squared, or 2a squared. The other right triangle that we set up goes from, we have a here, we have b here, c goes from the bottom left front corner all the way through the middle of the center atom to the back top right corner. And so here it's going to be a squared plus b squared equals c squared, but we already showed that b squared is 2a squared. So if we plug 2a squared in for b squared here, we get c squared equals 3a squared. We also know that this c right here, because every atom is touching here, this is 4 atomic radii. 1, 2, 3, and then 4. So c is equal to square root of 3 times a, and that's equal to 4r, or a is equal to 4r over the square root of 3, or r equals square root of 3a over 4. Useful to know this. So this formula, you don't have to derive this every time, but you're going to need to know this formula, and this. For a face-centered cubic unit cell, we just use the Pythagorean theorem once. So this is a, and this is a, and this is b. B is going to be equal to 4r for the same reason, because all of these atoms are touching. And so a squared plus a squared equals b squared, which is equal to b squared is 16r squared, And so A is equal to the square root of 8R. So those are the derivations, but like I said, you just basically need to know this formula, and this formula, and make sure you guys know which unit cell it belongs to. Alright, so let's do another example. Given that the density of niobium is 8.57 grams per cubic centimeter, and it's known to crystallize with a face-centered cubic unit cell, calculate the atomic radius of niobium in picometers. Right, so, you know the density, and you know that it's face-centered cubic unit cell, so you know the relationship between the length and the atomic radius. So go ahead and work this out and come on back when you guys get an answer. Welcome back. Let's look at this. So density is mass over volume, or volume is mass over density. Mass we can get is just the molar mass divided by Avogadro's number. The volume is the length of an edge cubed, or the length is equal to the cube root of the volume. Once we get L, we can get R, because we just saw those formulas. R is equal to the square root of 3L over 4. So let's first get the mass of a unit cell. So niobium's molar mass is 92.906 grams per mole divided by Avogadro's number. We can get this many grams, 1.5427 times 10 to the minus 22nd grams per atom. And remember, in a body-centered cubic unit cell, there are 2 atoms per unit cell. So the mass in one unit cell is 2 times this, which is 3.8055 times 10 to the minus 22nd grams per unit cell. All right, so now that we know the mass, we can solve for the volume. Just take the mass divided by the density, which we're given, and we know the volume per unit cell, 3.60 times 10 to the minus 23rd cubic centimeters per unit cell. The length of an edge of the unit cell is cube root of the volume, which gives us 3.302 times 10 to the minus 8 centimeters. And we were asked to get the radius in picometers, so I'm going to convert to picometers now. We could do it at the end, but I just did it here. And there's 1 times 10 to the 12 picometers per 100 centimeters. So the length of a side of a unit cell for niobium is about 330 picometers. And using this formula up here that we derived a few minutes ago, the atomic radius is equal to square root of 3 times the length of an edge of the unit cell divided by 4, which gives us 143 picometers. The real value experimentally is 146 picometers, so once again, not too bad. That's all there is to it, guys.